Welcome to another episode of Inference Time Tactics. I'm Calvin Cooper, co-founder and COO of Neurometric AI. We're a token engineering platform, and today we have our head of AI research, Yash Sharma, to talk about a really interesting paper, Pioneer Agent, Continual Improvement of Small Language Models in Production. For everyone listening who's not an ML engineer, me included, here's the setup. Small models are cheap, fast, and great at one job. The catch is getting them to do that one job and keeping them there once real users start hitting them. This paper says the bottleneck is not the training itself, it's everything around it. Small language models are attractive. However, adapting them to a specific task remains challenging as an engineering loop, driven not by just the training, but everything else: data curation, failure diagnosis, regression, avoidance, and iteration control. So Yash, what is this paper? Who wrote it? And why did it catch your eye?
Yeah, so this paper came out, I think, a few months ago. It caught my eye just by the title, for example. So SLM creation is something we're really focused on here in Neurometric. It's a great way of reducing costs for customers, reducing their tokens. That's something we can talk about. And this was a paper saying they directly built a system to do that. So it was definitely informative in that sense. Second thing was also the authors. So Fastino Labs is one of the main players that are in the SLM research space. And so seeing that they were very focused on this direction was also interesting, and we could get some useful learnings from it. In terms of, I guess, a very short one sentence on like what this paper is proposing, you could go about SLM creation in a lot of ways. And as you just said, SLM creation kind of sounds like it's just about training. Just train the SLM and then we're done. But as we know here in Neurometric, SLM creation, especially a product that could be scalable, where somebody can just hit it and then get an SLM out of it, requires a whole system to kind of orchestrate and set up actually making that creation happen. And so essentially, what they've built here is a harness. So just to define harnesses really quickly, you could call Claude Code a harness. You could call OpenClaw a harness. You could call essentially any system you build around a really powerful model to get it to do what you want it to do, you could call it a harness. And so this paper was like a very informative, assortment of best practices on if we want Claude Sonnet, for example, to be our ML engineer in a box that does the SLM creation for us, what are all of the nice scaffolding and systematizing to do in order to get it to be really reliable at doing ML engineering or building these SLMs, and then, of course, benchmarking that system to validate the results.
So to kind of frame the problem and opportunity here by setting the stage with what we're doing at Neurometric, it's not like you just take an SLM out of the box and it's going to be that useful for any business, right? You've got to think about the specific task, pointing it at that task. And so you want to talk about, without giving away too many trade secrets of ours, some examples or how we approach it today and then where we're kind of going next.
Yeah, so I'll talk a bit about what we've already blogged about. We have a Neurometric Substack, and we kind of talk a bit about what we're doing here. So I'll give one example. So there's a agentic task called CM Arena. CM Arena is something where we based our leaderboard offering from about last year on, where we benchmarked a bunch of models there and found that one single agent or one single frontier model doesn't rule across all tasks, across all axes. But you can also use that agentic task as a proving ground for small language models. Can a small language model even do this sort of task, a task that is very relevant to 2026 because it's essentially a sales rep task, and it's essentially an agentic task. And so what we found was that when we put an SLM and just put it at this task, point it at this task, it fails, in short. And the reason for that is I think something that's community wisdom nowadays, that the frontier models are very capable, and small models are less capable. And so it's kind of unsurprising that you point at a very difficult task, you get poor results. So then the question is, what do you do from there? And so you could say there's three different ways of going about it. You could do a thorough evaluation sweep, This is something that we do in our evaluator product offering, where you don't just try one small language model, you try many small language models, and you sort of systematize finding a small language model that works for this task, knowing that there isn't going to be, especially for small language models, any one size fits all for any of these tasks. The second thing you could do is improve the model. And we've done, I guess, two things in that direction. One is fine tuning. So exactly what's kind of addressed in this paper. This is the main way to improve a small language model, adjust it, modify it so that it's better at what you're trying to do. And so one of our earliest successes, even coming from a few months ago, was if we fine tune a small language model on a Sierra Marina task, specifically a lead qualification task, where you need to qualify a lead. If the lead is qualified, great. If the lead isn't qualified, why isn't it qualified based on the BANT framework? For this sort of task, naive small language model did not work. If we fine-tune it on examples, synthetic data we created based upon the actual agentic task, we were able to get 95% performance on it. So a small language model might not work out of the box, but if you fine-tune it, you can get to work on your task and get your task-specific SLM. And to briefly, there's other ways of going about it here, which we've also blogged about, where you could take an SLM, you could create a harness around it, where it gives it all of the necessary tools that it needs in order to solve this task, which can really help with some of the technical difficulties with working with small language models. That also works for not only like a Sierra Marina task, but even a GDP val task, a very difficult benchmark, taking a bunch of tasks which are relevant towards economic GDP, agentic tasks, and benchmarking frontier models on them, which is still competitive today. The most recent Gemini model posted GDP val as a benchmark. You can get a 4B, an extremely tiny model, to do one of these tasks if you just give it the right tools to work with. And then the last thing to say is, and this is, I think, going to be relevant towards maybe order some like future directions based on this Pioneer Agent paper, is there are different complexities of tasks. Like the tasks we just described, Sierra Marina, GB Val, these are hard. But there's also like, I guess, very useful repeated work scenarios that are not as difficult. For example, named entity regression, extract the entities from a particular document. These are, in some sense, tasks that predated LLMs and are tasks that are extremely, like if you're using Claude for such a task, then you're probably leaving a lot on the table. And so that's actually the kinds of tasks, more or less, that this Pioneer Agent paper focused on. It's a great place for SLMs to play. But at least here at Neurometric, we are definitely excited about SLMs don't have to just play in these simple tasks. Can we really do the innovation to make them work in these really hard tasks, agentic tasks like Sierra Marina, GDB Val, and things like that?
And one misconception we hear in the market is that SLMs aren't capable of outperforming frontier foundation models, which we moved really quickly from the R&D that Yash talked about to task-specific endpoints in production. So if you haven't listened to the last episode with Fletcher and Discovered AI, we talked a lot about how they had an implementation in production for resume screening. They're hitting the Frontier API. They're getting like 70% accuracy. They work with Neurometric, and we move them from not just improving the cost over 10x, but also improved accuracy. So we achieved 98.5% accuracy, which was better than the research that Yash just talked about and that we blogged about. So pretty amazing. So thinking about the paper, the Pioneer Agent does not just train, right? It acquires data, builds its own eval sets, trains, looks at results, and decides what to do next. Do you want to unpack a bit about that?
Yeah, so there's a lot to the paper. It's, I think, maybe a typical conference publication is about 8 pages of main text. I think this is maybe 25 pages of main text. So it'll be a bit difficult to kind of just wrap it all up into one narrative. I guess I can talk a bit about some of the main aspects, and maybe we could even like walk through some of these individual topics and go from there. So I guess just naming things off the top of my head and things that they had to deal with. So first of all, one of the things that was nice about this paper is that they first start with the pre-deployment versus the post-deployment scenario. So in the pre-deployment scenario, the cold start problem. And for example, it's very, it's academic research, but it's very customer-centric in that sense, where we want to build a good model for a customer before we have any traces or any data on how well that model works in production. And then the post-deployment phase, the production phase, where we put that model in production and we see where it's failing and then we fix it. And this is very typical ML engineering ops, where you want to build a model, and then when you deploy it, you want to monitor it, you want to fix failure modes. And this is their naive baseline. You just want to continually retrain the model when you're seeing it starting to fail. But then I guess, as Pioneer Agent is describing, if you retrain and do nothing else, you can lose a lot in terms of performance, which is where their agent comes in to try to fix things. So I guess to put it in short, they have one pipeline for cold start, pre-deployment, and a whole entire other pipeline for post-deployment. To try to wrap it up, what's similar between both of them is, again, they're using an agent to sort of orchestrate this whole process. They use Claude Sonnet 4.6 for almost all of it. It is relevant, the agent that they use, because they even have a cost analysis section towards the end of the paper where they're making the argument about how does this compare to, say, an ML engineer? If an ML engineer gets paid $150 an hour, for example, how does the cost of having this ML engineer in a box fare? And there's basically two cost sources here. One is that agent, so Claude Sonnet 4.6. If they used a bigger frontier model, if they use Fable 5, for example, then those pricings are higher, and then you would be costing more. The fact that they got this out of not even Claude Fable 5 or Claude Opus, but Claude Sonnet indicates that you don't really need, as an agent, as an ML engineer box, the most frontier model in order to get good performance. And that really helped them for making a cost argument, because using Claude Sonnet 4.6 really helped with that. The second source of cost is the actual ML engineering here. So Sonnet 4.6 is kind of proposing a plan, being the brain, essentially, sort of deciding what we do. But then really what it's doing is it's orchestrating experiments. But we need to run those experiments. And as we described before, the main way of making task-specific small language models is to train them. And training models often requires accelerated hardware, so GPUs, for example. So what they've used for that is they use a modal sandbox in order to kind of isolate their actual development, so that they're always experimenting in like a containerized, not a very wishy-washy environment, always the same environment, which costs like 50 cents an hour. And then second of all, they're using the Tinker API from Thinking Machines, one of the big AI research labs that has really looked into fine-tuning and has developed not only a toolkit for fine-tuning, which we can talk about. It's called LoRa fine-tuning, which is an efficient version of fine-tuning, but also a platform where you pay them a platform fee and you can do your fine-tuning there. And so if you add up all those costs, it's like half the cost is Claude Sonnet, and then half the cost is paying Tinker for fine-tuning. It's well below what an ML engineer might charge for doing the same sort of work. So that's, I guess, maybe like at the meta side. Now, what is actually happening? So Claude Sonnet is given a set of tools, both in cold start and production. The main difference I would call out for what's happening in cold start versus production is production's operating on real live data that you're actually getting from the customer, traces. And you kind of have to orchestrate a system to work with that. Cold start is like, how do I build a model without that? And so for that, there's actually some similarity between how they're thinking about the problem, how we've thought about the problem. In the cold start scenario, you might just start from a generic task description, train a model on this kind of task. And you just have to work with it. The question is, how do I take some generic task description and get a model out of that? And of course, a Claude agent can take that task, and start thinking about what to do in that case. So really, the first step often for training a model is getting data. And so that's, I would say, is like the primary thing. And that's, of course, lots of deep dive topics within this paper. That is one deep dive topic of setting up the system. But maybe I'll start at the high level. At the warm start level, you're taking public data, for example, from Hugging Face, and then you're training a model on that. You're curating that data in an intelligent way. You're just using Claude Sonnet's intelligence to try to do intelligent things when working with the data. Be an intelligent ML engineer. And then, for example, and so you need like a web search tool in order to actually get that data. Train that data. If that data doesn't exist on Hugging Face, then use synthetic data, something that we've been also doing as well. If the customer comes in and like has a task that there isn't really any public data set for it, just ask GPT or DeepSeek, for example, to create synthetic data. From there, you now have your data. You now need to train the model. There's so many ways to train models. And that's one thing that they actually look into, like a search algorithm, for example, to have Claude sort of iteratively try out many different ways of training models, different branches going different, like multiple iterations in the same branch and kind of deciding this branch is promising, this branch is not promising, sort of ending up somewhere. And then on the production side, it's a lot of tooling like, for example, maybe your production data is in a SQL database, for example. You want a tool that can allow you to query that database because that database could be 10,000 rows. And then you're feeding all of that to Claude Sonnet. Not only can it get confused because now its prompt is huge, they can also just spending so many tokens, just put all of those rows. And so building tools for that. So in short, for these different types of problems, the cold start problem and the production problem, they're trying to get Claude Sonnet to be the ML engineer in a box, and they're building tools and building a harness to kind of direct it in a way such that it's good at each of those phases. And of course, there's lots of minutia and lots of details in how they architected different aspects of the cold start phase and the production phase.
I think that's a really good point. And this really illustrates why so much of the value is in everything around the model, right? And this is partly why you'll start hearing Neurometric talk about ourselves as a token engineering platform, right? Because fine-tuning small language models, there's a lot there. This is just the tip of the iceberg, and there's so much more to do. But when we talk about impacts, right? So in this paper with the cold start problem, we saw improvements of 1.6 to 83.8 points over base models across 8 benchmarks, right? So that's an enormous range. What separates the task where this barely helps from the ones where this transforms the impact?
So it's actually quite simple. So the 1.6% case was a case where the base model already worked well. So base model is getting 90%. The Pioneer agent got it 91%. So you got like a 1% change. In the case where you got an 83% change, the base model was terrible. The base model got like 10%, and then Pioneer agent got 90%. So they even call this out, that the Pioneer agent is good at just making sure that your small language model at the end of the day will be good on whatever benchmark you have. And they have all these heuristics in-house where it's like, the default for good performance is like 90% performance. So Claude, for example, keep iterating until you get 90% performance. But Claude, also use your best judgment for like this kind of task. Maybe Claude does a literature review, for example, reads a bunch of papers on this topic and sees that state of the art is actually 50% and not 90%. Feel free to use whatever you learned from your web searching and your literature review to like reassess that. That maybe we don't actually aim for 90%. It might not even be possible to aim for 90%, aim for 60% then. But in terms of actually their results, it seemed like across all of their benchmarks, they were able to get 90%. It's just that if the model is already at 90%, there's not much they're able to do to get it from 90% all the way over the hump. You could say that's like the long tail in some sense, that model's already 90% good. How do you get good in that past 10%? It's actually quite hard. But going from 10% to 90%, it's likely due to some fundamental basic things. So for example, there's like issues with output format. So like when you run an evaluation, if that evaluation expects that the model should output a JSON format with a particular key here and a value there, the model could be doing something smart. The small language model, and we often see that actually in practice, that small language models, you might look at that score of like 12% and think, oh my God, small language model is terrible. But then if you actually look at what it did, it seemed to do something intelligent. It just was inconsistent. Maybe it wasn't matching the output format, things like that. And so a Claude Sonnet agent can look at that, look at those failures and be like, okay, the small model doesn't understand that it's getting the right answer. It's not putting in the right output format to be scored correctly. And so let's tell the model, or let's fix the model. Let's give it data. A lot of this here is Claude Sonnet creating data to fine-tune the model. So you'll create data with that right output format, fine-tune the small model on it, and now suddenly it goes from 10% to 90% because now it knows the right output format. So there's little things like that to get it to pass benchmarks. There's always a question as to whether that actually matters in production or in practice. But you can also imagine that, let's say you're fitting the small language model into a whole system, and that system does expect outputs in a particular format. That's a real problem. It's not just an academic problem, but it's a really simple problem that just fine-tuning a model and having a frontier model analyze what's going on and then create good data to fine-tune the model can clearly fix. And we can see that in terms of the benchmarks in this paper.
Yeah. So as you mentioned, Yash, like that tail end is really, really, really hard. So getting to 98.5% accuracy in production with customers is absolutely amazing. And what we're hearing in the market as people come to us is often people are trying this themselves. They're like, how do I lower costs? Token engineering, token maxing, these terms are now top of mind. You even hear about it on CNBC now, and a year ago nobody cared. People were like, why would anybody ever care about this? So we've been pretty ahead of the curve, but it turns out specialized intelligence requires specialized talent to really develop solutions. And the paper kind of goes into what can go wrong, like naive retraining, degrading performance. Do you want to talk a little bit about that?
Yeah. So, I mean, I guess Fastino, I think they alluded to there are some real world use cases that inspired what was going on in the paper. But in terms of the benchmark was mainly, say, like they had to create sort of like simulated sort of scenarios for production scenarios. And so one way they did this is they created a stage-based evaluation where for actually evaluating the production side, as we said before, they have one harness and one system for cold start, and then they have another system for production. In the production scenario, the way they try to simulate it, they also, I think, is not just an element of making it real world, but also an element of making it hard as well to show that the system is actually quite good. And so one way they did that is that, I guess, the realistic aspect here, which is essentially the basis of why the Pioneer agent did so much better than naive retraining, is that when you have production data, the production data can be very messy and noisy, and might not be reliable. And so the way they simulated this is they poisoned some very clean data at like 10%, 20%, 40%, made it noisier and noisier. So that's the hardness aspect, where they just kind of upgraded like how messy and how noisy the data is, just to see that like how well does the agent do versus naive retraining. And what you can see there is that, in short, naive retraining is going to train on that noisy data. But that noisy data is unreliable, 10% unreliable, 20%, 40%. So of course, as that gets more and more unreliable, naive retraining performs worse and worse. And so if your system was just that, then your system can absolutely fail if you're dealing with a customer who's in a very real scenario where they haven't completely cleaned up their data. And honestly, that's a whole job in order to clean up your data. And so in this case, the customer doesn't need to clean up their data. If you feed this to Pioneer Agent is essentially Claude Sonnet. Claude Sonnet can look at that data and train a model on it, for example, see that the model, and of course, they have this whole search algorithm sort of thing where they train many different configurations in parallel, and then they see what's promising, as we saw. But it will essentially very quickly detect that there's something wrong with this data set. What is wrong with this data set? And then now you'll see the amazing frontier capabilities of frontier models, where it starts to reason and starts to think about, like, what is this? Find, for example, the actual failure scenario, figure out what's clean data, what's bad data, remove that poison data, and then now train the model. So essentially, it's just demonstrating one scenario where putting this sort of ML engineer in a box, where you don't just naively retrain, but have an ML engineer box, which is now Claude Sonnet, to actually look at your data and do something that an ML engineer typically does, which is look at the data, figure out what's good data, and train on that. And of course that helps, and this demonstrated how much it helps, a 43% improvement, because just kind of siphoning out bad data, which can often occur in, say, a production workflow.
Yeah, so this is really a living AI system. You can't just evaluate on a static benchmark and snapshot and call it a day, right? So this paper simulates a deployment over time, which is really important. So unpacking what else in the paper really stood out to you.
Yeah, so I would say a couple things. So one, maybe to get into another, there's so many details in this paper. One other detail, because it's just interesting how they went about it. I guess a couple other details. So one is, in the production scenario, you're starting from the cold start model, and you're really iterating on that model. In the cold start scenario, you're starting from scratch. And so again, one difference here, but they're really accounting for it in how they set up the system, where in the production scenario, they have a regression, rollback, essentially. So if we do an iteration, we create a new model, and the model seems to be performing more accurately, let's be a bit more mindful here. Let's check the success cases or the failure cases of the previous model and make sure that this new model is still getting that right, so that we don't get like unexpected scenarios in production where, oh, you gave me a better model. This is 93% accuracy of 91% accurate. Then why is it getting this thing wrong when before the model from last month was getting it right? So they directly bake that into the system where it is not good unless it passes the regression test. If it doesn't pass the regression test, this is bad. I don't really even care about the accuracy at that point. Roll it back, start over. And so this is also why the system can maybe take 10 hours, for example, on a problem, because it's doing all of these iteration, all this testing, and they're really being very, very precise and very stringent with this is good enough for production. Another aspect here is, again, they're really indicating with all the details in the paper that it makes sense to put Claude Sonnet as an ML engineer in a box and just deploy it. But again, nothing's as easy as that. We have 20 pages of details about how to help Claude Sonnet be a reliable system. So one example here is that let's say we got some accuracy, right? And the accuracy is bad. They do have a direction there being like, don't just do anything. If the accuracy is bad, it's probably a data problem. Look at the data first. If the accuracy is like 80%, and again, they're being very precise, accuracy less than 80% is bad. If it's less than 80%, look at the data, because that's often the problem there. It's bad data, bad results. If accuracy between 80 to 95%, data is probably fine, or else you wouldn't really get 80%. But if we want to get better, it's probably the hyperparameters. Hyperparameters is like, what is the learning rate? All these fine-tuning minutiae. It's probably the details here that can get us a bump in performance. If you're already at 95%, and of course, this is also where it was challenging. We already discussed that like they have a hard time getting past there, but they did try to go from 95% upwards, which is, okay, if you're at 95%, only 5% of the eval you're getting wrong. Focus on those 5%. Maybe create some synthetic data based on that 5%. So they're really directing the model in all these different regimes as to, and really baking in ML engineering best practice into the prompt, into the harness for Claude Sonnet, so that it's as good as the ML engineers at Fastino, for example. Whatever the ML engineer can think about is like, the model should do this, bake that in. I guess the last thing to say in terms of maybe something interesting for the future would be, I'll say two things. So one is when they looked at some of the limitations, for example, some of them are kind of expected where, let's say, for example, the model Claude Sonnet looks at the SLM and finds that this model, 90% of its failures is because it has some clear hallucinations and has some clear errors in its knowledge base. If you want a really cost-efficient system that runs in 10 hours on like way less than ML engineer in a box, it's going to be challenging to repair that problem. So this was one case where the Pioneer agent failed, where if we need a full retrain of this model, not even just a minor modification, like the model is just completely bad, then maybe this is more expensive than the bandwidth that we've given the Pioneer agent to run in production, because we want this to be cost effective. So these are all sort of expected. The one thing that I think we can definitely relate to here at Neurometric is under specification. So as we said before, that idea of giving this task description and kind of just like jump starting from there is like something that we've thought about as well, because it puts the lowest burden on the customer. Just kind of describe your problem in words. And we'll just give you something. But of course, as we know, if you describe your problem in words and we give you something, there's so many words you haven't said, essentially. And so we'll give you something for those 5 words you said, but if there's 45 additional words, then we got to iterate with you and add those 45 words and that sort of thing. And so they even saw that in their practice, that if they, for example, create a model based on a particular prompt, and then in deployment, the prompt is completely changed, then of course the model will start to fail because it's a task-specific model. But of course, in that scenario, we can just work with you to like adjust for that change and modify that and move in there. Like nothing is free in this world. So if we have an extremely tiny model, we do need to like adjust. When you change your deployment, the model needs to adjust with it. And that's definitely something that can be caught with monitoring, for example, monitoring drift. Last thing to say is that if you look at the benchmarks in this paper, one thing that we've been working on a lot at Neurometric, which I've already hinted at before, is moving small models from this idea, right? Like what is a community idea that we feel like is wrong, that we want to change? And one basic community idea is that small models bad, frontier models good. And of course, we've done a lot of work to show where small models are valuable. And when small models don't work out of the box, what we can do to fix them. We have lots of success cases there. But even going further, even for the people that accept, like maybe Fastino Labs, for example, that small models are good, cost-effective solution. There is this other like sort of idea there where they're good, but not for complex problems, for very simple problems. And you can see that in a lot of the benchmarks here in the paper. So they looked at named entity recognition, as I said before, a very basic problem from NLP world where we already know small models can do well in those scenarios. They looked at, for the LLM, the small language models problems, they looked at a lot of these old benchmarks, which are essentially Q&A. Trivia QA, for example. What is the tallest mountain in the world? Mount Everest, right? And so these are valid problems that can absolutely come in production. So it's very valuable. But we also want to see what's the next frontier for small models. How can we go further? And nowadays we're seeing things like OpenClaw, for example, where we have fully agentic workflows, where we need the model that powers it to be able to search things on your computer, schedule a calendar invite, send emails, and even at face value, and also even at a technical level, this is a lot harder and a lot more unconstrained and a lot more general than what we were dealing with before. And in some sense, it's really like pushing the limits of task-specific models, because you can imagine this is very much a great scenario for general models, because OpenClaw is a general scenario. And so one thing that we want to do on the research side is, like, in very hard scenarios where we're our backs against the wall, trying to make a progress there. And so I guess calling out here that we've been doing a lot of internal benchmarking and building up an SLM creator system that can do work actually even in OpenClaw or agentic scenarios, potentially getting into your Claude Code scenario or your Claude Code harness and working in these real agentic scenarios where Anthropic and OpenAI have been winning the day. But if you looked at Pioneer Agents benchmarks, a lot of their benchmarks was those like trivia QA sort of scenarios. And so they even say in terms of limitations, if we go beyond the settings that we studied, we're going to have to do a lot more work. We're going to have to do a lot of engineering to make them work in those scenarios. And so I guess what I'm saying is that there is a next frontier for small models. Even if we accept that small models are useful, small models can really be pushed even towards the hardest sorts of tasks. These are things that we're working on in Neurometric. And it's something I guess the SLM community should be working towards. SLMs are not just reduced to simple tasks. If you make a lot of effort, you can make SLMs work even in the hardest tasks.
And we're starting to do that now. Like, we just launched a partnership with LumaDoc, helping OpenClaw users cut their costs by 90%. We released OwlWatch, and there's so much more coming out. So if you're interested, we often blog about these things in real time on our Substack. So neurometric.substack.com. And if you enjoyed this episode, please be sure to like, subscribe, and share. We'll link the paper in the show notes. And thanks, Yash, for diving in. And thanks to all our listeners for listening in to another episode of Inference Time Tactics.
Of course. Great to be here.